Sorry, it's been a little while. Doing a lot of testing, making sure I had the cleanest version of both of these necessary components. What we're going to be doing is making it so we can look around in all directions. If you had a 6 degrees of freedom cam or just the normal Z up, Z down cam like the one that I have here, it'll be able to handle all directions and smoothly interpolate itself to your forward direction or pick up the speed if it's more than 180 degrees. It's got some smooth turns too, depending, but it's a highly tweakable system, and it's got some pretty fun values you can mess around with. So I'm going to teach you how to make it. Here's a sample of what we'll be doing first. So this is the this is the torque dampening function, and I've already made it here, of course, but I'm going to show you how to make it. So what you want to do is just go ahead and make a new function, call it torque dampening. And I'll cheat and I'll just go over here and show you how this one is made. So for the torque dampening, the actual inputs here are important. So I have primitive component for the first one. Input pin for the second one is just going to be a vector. And yeah, that's all you actually need. So the vector and then the float value. What the vector value does is tell you how much torque dampening you have in each direction. So that's if you want to be able to tweak that. Just go ahead and have that input there. And then the float is how much overall dampening we're applying. Once you have all three of those from the primitive component, so let's say if you wanted to do this directly, the primitive component would be the capsule. Check is simulating physics. Get a branch. And if it is true, then we're going to execute add torque in radians. Add torque in radians. From the capsule component again, get world transform. That's the wrong one. Let's turn on the context sensitive, and we'll need the scene component version of this. Get world transform scene component version. Get a inverse transform direction. And from the capsule component, get physics angular velocity. In radians. Connect that to the direction. Vector, get absolute. So just get absolute vector. Multiply. multiply it by the inverse transform direction. Multiply again. You'd multiply this by your vector. So we can just get a temporary torque vector. Let's make this a vector, but you would just be using the input from here. You could just connect that directly. You don't need to do this. But just for example's sake, here's the way that you would connect it up here. But let's just say we have a torque vector here. Let's have 1 for all the values. And add one more multiplication, and that's going to be your float value. And I can just do a multiply float. Four. And that's going to go into your transform direction. We can just search for it here. So not the inverse, but the normal transform direction. Put this multiplication into the direction, and lastly into the torque. You might want to clamp it though, so let's put a clamp vector size. Right here I clamped it to 100. Seems to work pretty good. Negative 100 and 100. And check acceleration change so it can actually slow you down. Alright, cool. And that's how you make it. Once you have all that, it'll well, it won't work just yet because you're gonna have to make sure that this value down here is negative. So multiply this by -1, and then you're good. Now we have some torque dampening, and I'll just leave the way that I have it connected up here exactly the same and not change that. But that's what we're building. And do put it in a torque dampening function by itself and add those inputs. Like I said, here's how you add those inputs just in case you don't know. You can just do the plus here and then search once you have the input there. Click the drop down and then find a primitive. Primitive component, there it is. Get the object reference. So that's the first one. Second one is a vector, and it was a vector type. Third one is a float, and that's a float type. So that's all I did. And then if we wanted to like connect this, just grab this. This is what it would look like. Just connect these. And then the torque vector, we can grab this. And float, we can go and grab this and put it into the negative. No longer need this temporary torque vector there, and that's the way it's made. Oh, and for the add torque and radians, you do need to connect the target, which is going to be this primitive component as well. And now we're good. So either one of those work. I can use the torque dampening that we just made, or I can use the one that I already have here, but it does need to be changed to one for all the vector values here, and the float would need to be something like 4. But okay. Next, what we would need is this difficult function over here. So this is the compute look function, and it tells the capsule which way to turn based on the camera direction, and it's using quaternions, so it doesn't mess up over the 360 degree mark, or 180 degree mark, I mean, when it flips the z-axis. What it's doing is, once it flips the z, it checks to see if the quaternions are greater than or less than 0, and it flips it by itself to either -1 or 1, depending on that. So I'm going to show you how to build this so that you can have a system that looks like this, and you can look in all directions freely and change those values. So if you want more torque or you want more dampening, you can easily do that. So we're going to build it the same way that we did last time with the torque dampening. I'm just going to pretend to make a new function, but I'll have this up above just so that we know what we're doing the whole time. And first we're going to need a few values here. I've got some extra stuff that you may or may not want, but I would just add it in just in case. So first and foremost is the actual target and the origin, which is just going to be the capsule and the camera. So I'm going to grab the capsule component here, get capsule component, and let me see what I have connected for the camera. I've got the follow camera here. So make a new function, by the way. Be sure to make a new function, call it compute look, and this is what you're going to be adding to it. So get the capsule component, and then of course is simulating physics. You're going to want to check that first, get a branch out of that, and then if true, we can execute our add torque in radians. That's what you want. And then we can just move that all the way down a little bit to the end and start doing the rest here. So we also want, for the second input, we want the follow camera, and that's going to be a scene component if you want to do the input for that. Scene component here. Then we want a input vector. We can just, the way I'm going to do it right now to fake it is to do an add and then change this to a vector value. And this is for future proofing your directional look. So what this is going to do, the reason I'm having the input vector into here, even though it's using the camera direction to decide the look, is you can change your orientation. Like let's say I put 90 degrees and then the input vector is, I don't know, 90 or something. It would change your actual look direction. So if I base that on the actual like forward vector or something like that, it would be a lot more stable. But it's something cool you can do. You can mess around with the directional looking and stuff. So let's just zero this out. But all right, anyway, we're gonna want one of those and get a camera as well, and we need the rotations. So get the world rotation from the camera and get the world rotation from the mesh as well. get world rotation, get world rotation. And we'll just leave those there for a second. And the world rotation from the camera, we're going to do a combine rotator. You could just directly get this and then get the quaternion out from it, but I want to do this instead. So get a rotator from axis and angle. Rotator from axis and angle. Put that into the B. And then the angle amount, let's just get another add and pretend that that's going to be the input. We can just leave these 0. These two inputs are going to be how you turn and switch around your orientation using WASD if you want to do that. That's why it's a combined rotator. But okay, we have our two different parts of this equation. We're going to make two different quaternions here. So 2 quat for quaternion, or just type the whole thing in. 2 quaternion rotator. And then we need another one of those for this one down here as well. And we might want to break both of these quaternions. So let's get 2 break nodes. Copy it. Let's put a node before each of these because we will need the raw quaternion value for a few things as well. And what we'll need it for is to get another break quaternion. We can just put that over here up top. And then the bottom one, we just need it for a inversed quaternion. So we can go ahead and get that now. Let's go ahead and organize just a bit. Cool. All right, and now we'll want to solve the flip, the sign flip for these. So just multiply everything by each other. We're going to need 4 multiplications for that. So x times x, y times y, z times z, w times w. And then we just add those all together using one add node here. And then check if it's greater than or less than 0. So add, and then just use the plus right here for add pin. And then we can get 4 different nodes to use. Get the less than node for 0. And we're checking to do a select float node here. And then we're going to multiply it again times the quaternion. So let's pull out from the less than, select float. Let's do -1 and 1 for B. Now we'll want the same thing, so 4 multiplications. Let's put it into x, y, z, and w, and then do this select float node for each one. And we're going to pull out another node here just to organize it a bit. Multiplied by everything. And now we can make a quaternion here just to combine everything back back together into a usable value. Once we have this made quaternion, it'll be able to be multiplied by the inverse quaternion from earlier. So we can get that a bit closer. Good. And now that we multiplied it, let's just go ahead and break the quaternion again. Get the break quaternion node, and we're going to make a vector out of it, splitting off the W to be on its own, and the W itself is going to be going into a tangent node here. So let's get the vector length first. A tan 2 radians. And after we put the W in, we're just going to multiply that by 2 or 1, doesn't really matter. I would do 2 though. And check and see if it's less than our dead zone. And we're almost done. Less than. And let's get ourselves a dead zone amount. So we have our angle. Dead zone will come right after. Let's just get another float. Go all the way down. Plug it in. W is going to go into the tangent. Good. All right. We can do a select float out of this less than. So select float and multiply that. We'll get the multiplication here, the multiplied by 2, and put that into the B. And this value here, we'll want to clamp this so that it's not out of control. So clamp float, and then the max is going to be pi. So just get pi. Context sensitive. There it is. Good. And we can multiply this by our power amount. So we'll need another input node for that, for power. And that's going to be a float as well. And of course, we'll want to clamp that one more time. So this final final output here, let's clamp float, and then the max is going to be our max power. So we'll need one more node for that, of course. Good. And yeah, now we can just multiply these together and get our final value. So over here where we made the vector, let's get this and multiply it by our new W, is what I would call this. And we can put that directly into the torque, but I would still do a clamp one more time. Clamp vector size, maybe do -200 or something. 100 would probably be smoother. That's why I did 150 before, now I remember. Yeah, negative 150 to 150. And we can acceleration change this as well. And that's all. So now we've got all that. And if you want, I'll show you how to get this plugged up inside of an actual function, as well. Let's just call this compute looking. Already have compute look. And let's copy everything we did here. Now let's make these inputs to show you how to do it. This is going to be the capsule. It's a primitive component. It's going to be a camera. That's a scene component. Vector. It's just a vector. Angle. That's a float. Dead zone. Power. And lastly is max power. It's going to make some nodes here. Let's go ahead and connect try to connect everything. So capsule, camera, vector, angle, dead zone, power, max power. Good. All right. And then connect the execute pin. And you're all done. Cool. Now that should work just fine. And I'll show you. Oh, you'll need the target connected. I always forget. Let's get the primitive once again. Connect the target. And we'll just get that compute looking. And I'll show you how to get these working. So, of course, you need the capsule component again. For the capsule. Let's connect the torque. Oh, actually, I'll do this from scratch. So, yeah, get the capsule component. Get the camera as well. Connect everything. You can leave the vector and angle 0 on this. Dead zone 0. Power, I put 300 last time. Seems to be good. Max power 150, so really it's just 150 power. And you want these to be activated on tick, so you can create a couple of functions for them. That's what I did. I just did a custom event, add custom event, and just connect it. You can call it looking event, something like that. Torque event, and then once you have those, you go up to your event tick and just add them there. So I'll make some more room here. Looking event. Torque event. I can disconnect these old ones, and let's just make sure our new functions work. All right, looking good. And nice. So it works exactly as intended. It doesn't really, it doesn't mind however you flip and turn your camera. It'll always find its way back to the front. And it's a pretty fun system for not only like character flight, but it works for spaceships and stuff like that as well. You can tighten it up with some of the values here. I'll show you a little bit about how it works. So if we want it to be a bit more like loose, we would just turn down the dampening amount, the float, turn it down to 2. And then you'd have that a bit more floaty. Takes a little bit more time to get to the center. But with more, let's turn it up to 5. It's a bit more exact and tends not to overshoot. Even when it goes pretty quick. Feels pretty good. And this is just how fast it can potentially go. Let's see, let me turn this down to 150 as well for the power. That way it has a little less potential on the swing around, you know what I mean? Yeah, and it's a very easy, very clean, tweakable system with a lot of potential. So hopefully everything worked out for you pretty well. If you have any questions, leave them down in the comments below, of course. And look out for the next video. Tell me what you want on the next one. What other tutorials do you want to see? I'm thinking about possibly expanding this into like a superhero tutorial where I do fighting moves and different things, how to do those animations, how to animate inside of Unreal Engine, whatever you want, just let me know. But all right. Thanks for hanging out for a little bit. Subscribe if you haven't already, and see you in the next one.